Okay, I'm going to pick up where I left off in real life just a couple minutes ago. It's too exciting to shut up about. I was just talking about how Newton said that, or thought that for the universe to not change, for it to remain up and not all collapse in a big pile due to gravity that he discovered, it would need to be infinite so that there'd always be somebody over here to pull you that way to make up for somebody pulling you this way. Essentially, it amounts to this: an infinite distribution of matter has no center and doesn't know where to collapse to. And so I guess it wouldn't collapse. Newton was desperately trying to keep the universe from changing. Um, ah, my excited little doggy getting her. See that? And my other excited doggy. Okay, with that distraction, we'll get back to the universe, which is full of dogs, stuff like that. In any case, what I want to get at is some things that are universal here. I mean, I'm sort of toyed with the fate of the universe and whether or not it should collapse. I want to come back to that. But first, speaking of collapsing, follow this line of thought. What if you had a star and it's super duper massive and it loves itself so much, it's always crushing itself, and it's fighting back with nuclear fusion or whatever sources of energy it can muster to withstand the onslaught of gravity. But you know, you run out of gas eventually. Eventually, you run out of things to fuse. Maybe you get desperate and fuse something else. There's a whole story about if you fuse and fuse and fuse things until you get something that don't do any good or don't do any good to fuse, like iron, then the core collapses. And there's one thing that can happen in a core collapse, which if you take astronomy, if you want to hear this, the cataclysmic, sudden, just like that fast collapse of the core of a massive star can lead to an explosion there aren't even words for. Humongous, don't even come close. It's called a supernova. And a star can blow its outer layers to kingdom come in this titanic, that's kind of a good one, titanic explosion that sends debris out through the universe that eventually recollects to form about everything in this room. Yeah, you're made of stardust, largely. It's quite a story. In any case, let me back it up a little bit. What if the star is collapsing and even that can't happen? What if no force can fight off gravity? Then the star will collapse to phenomenal density. Back in 1700 and something, I believe it was the late 1700s, somebody, I forget his name now, was using Newton's law of gravitation, was thinking about escape speed and did this. Said, what if escape speed, which is the square root of 2gm over r, like that. What if escape speed got to be 3 times 10 to the 8th meters per second, which is the speed of light? That means that light itself, which goes the speed of light, could barely escape. And if you upped the mass anymore, or brought the r down or made it smaller or more massive, either one, escape speed could exceed the speed of light, and then light couldn't escape. Any light that fell on it would fall on it and never come out. Anybody on the thing who tried to shine a light out, the light would never come up to see you. And so what would this object look like to you if you're watching it, looking at it? You wouldn't see it. It'd be black. It'd be a, black hole. So the concept of a black hole really came up back in the late 1700s. Now, it's kind of fanciful. I mean, nobody could imagine what kind of a thing could ever do this. And so it kind of fell by the wayside. People didn't talk about it for a really, really long time. It actually wasn't until about 1938 that anybody really took it seriously. And when they did, they realized that one way a black hole could occur is indeed a star could collapse on itself after running out of fuel. And in fact, I'll tell you how much the sun would have to collapse. The sun right now it's almost 1,000,000 miles across. It's about 4 times as big across as the distance from here to the moon. And for it to become a black hole, it would have to be crushed down to about 3.5 miles in diameter and phenomenally dense. It'd be like, I was going to say unearthly. Of course it's unearthly. It's like way beyond anything earthly density. And then it would be one of these things. And light couldn't get away, and neither could you. And I'm going to talk about Einstein in a few minutes. Yeah, that's coming up. Nothing can go faster than light anyway, so nothing can escape. So a black hole is a pretty frightening thing. But before I can really talk about a black hole in a good way, I have to mention something else. The theory of gravity. I mean, I told such a long story. We went through all this stuff. Come up with Newton. Newton's so triumphant. We got this incredible law of gravitation, you know. Surely that's the end of the story. Of course not. It's the never-ending story. Is that a film you knew? Anyway, so there's more. It turns out there's some tiny things wrong with Newton's theory. Remember how there were some tiny things wrong with, you know, Copernicus even, that took Tycho to recognize? Well, there are tiny little things, like the way the orbits move around a little bit and things about light bending around the sun. Some of these things were known before. Some of them were predicted afterwards. But let me say something about Albert Einstein. Albert Einstein came up with a theory in 1960. It's really an extension of something he did in 1905. It's called the theory of general relativity. And yeah, it's Einstein. You know, the guy who waved at my niece's husband's mother when she was trick-or-treating there? Yeah, him. Yeah, he did. Bedroom slippers. They did her. Anyway, so Einstein comes up with this. Let me, obviously, in the context of we're doing little videos and limited time and, you know, whatever going on with this, I can't tell quite the story. I wish I could, but I got to say something. Let me put it this way. You know, we made D versus T graphs. And if we made a D versus T graph, this is way back. If we made a D versus T graph for an object that's falling, it makes, you know, a curve because it accelerates, right? It accelerates. And so all these points, you know, little numbers you could figure out. So what if and why does it do this? Why does it accelerate? You know why it accelerates, because there's a force on it. F equals ma. Newton can explain that, sure. There's a force on it. And then you go like, oh yeah? How does it work? Well, you know, gravity. Well, how does the earth pull on things? And Newton says, hypothetico non fingo, which means I don't have a clue. That's Latin for I don't have a clue. I don't frame any hypotheses. Newton had no idea how in the world gravity was supposed to pull on things. It didn't have any hands. How does it do that? He didn't know. I don't really know. Einstein wondered, and Einstein kind of knows, but it's a little bit different way of looking at it. Imagine taking this graph, and I'm sure I'm going to do this wrong. I don't at all think that I'm drawing the graph correctly, but you know, you could take this curve and, I don't know. One day I'm going to like figure out exactly how I should have done it. You can make a really messed up, warped graph and draw a straight line on it. And it's entirely possible, and I probably didn't do it right, but it's entirely possible that these points would be the same as these points. It's just instead of having a curved line on a straight space-time graph, you would have a straight line on a curved space-time graph with the same information. In terms of an explanation, it means instead of saying that an object accelerates when it falls because of a force, you can say, no, it didn't accelerate. It traveled in a straight line at a constant speed. Wasn't no force on it. It's just traveling in a warped space-time. So Einstein says gravity's not a force. He says it is an effect of warpage of space. What on earth does it mean for space to be curved? It means lots of weird stuff. It means geometry. You put in geometry that you learned in ninth grade that Euclid came up with about 2,000 something years ago would be off a little bit. You know, triangles, the interior angles wouldn't be 180 degrees total. It might be something else. I can do that. I can show you something like that right now. Here it comes. Look at this. I can make a triangle on the earth. It can go down to here, over to here, up to here. I might do 3 right angles that made a triangle with maybe 270 degrees in it. And it's a triangle. It doesn't add up to 180 because instead of being on flat paper, it's in a warped space. That is mind-boggling stuff. I don't pretend at all that you're supposed to understand it here. I just can't help but tell you, because I wouldn't have told really the whole story if I didn't tell you that Newton was wrong, kind of, a little bit. Oh, we got to the moon on Newton's theory, but we need Einstein's for, actually, need Einstein's for GPS to work right. We do. Anyway, his theory that space is curved has some weird things going on it, and that I'm going to make some videos for another class later. I'll probably tell you about them so you can go back and learn this if you want to. Things about time dilation, weird stuff. Some of you are going to be fascinated. Others is like, I ain't listening to that. That's okay. You don't have to. But I like to tell the story of special relativity, and this is kind of branched off of it. Anyway, there's this weird thing called time dilation. When you get in a strong gravitational field, time slows down. Quite literally, time goes faster upstairs than it does downstairs in a building. Not much. The difference is minute, but it has been measured. Super accurate clocks have been synchronized, and one up on, say, the 6th floor of the building will run fast compared to the one downstairs because time is passing more quickly up higher in the weaker gravitational field. Now, that means time passes slower in a stronger gravitational field. You in a strong gravitational field? Not a black hole. It's intense down there near a black hole. I'm going to tell the story right quick of how, now with Einstein's theory here, there's so much more I could say. It turns out the Newtonian stuff I did to come up with a black hole is insufficient. To really describe the conditions around a black hole, you need general relativity. This was done first in 1938 by a guy whose last name is Schwarzschild, and then later it was done by a guy named Kerr in 1962 for rotating black holes. I'm getting too technical here, but let me just tell you the story of what it's like for you and your friend to be hanging around a black hole. Okay, it's like this. Like say there's a black hole, you can't even see it, you know, it's black. And here's you and your friend. Y'all got space suits on so you don't die because you're in space. Your space suits, whatever. And you're talking on the radio and you got super duper jetpack thingies. And your super duper jetpack things are going to keep you from falling into the black hole because it's trying to pull you in. You got this thrust keeping you away. You're talking to your buddy there and you say to your buddy, dare you to turn your jetpack off. Think I'm crazy? I ain't turning my jetpack off. I'm going to fall into that thing. Dog dare you. You're crazy. I ain't doing it. I ain't doing it. Nobody can make me. I double dog dare you. Now, I mean, I know a double dog dare, you got to do it, but that's a black hole. Triple dog dare. That's it. That's it. I mean, it's a matter of honor. Yep. So you turn off your jetpack. Well, this is your friend. Your friend turns off the jetpack. You watch your buddy plunge toward the black hole. Ha! And as they plunge toward you, listen on the radio because you got spacesuits and helmets and radios. And you listen, and your friend tries to yell, help! But instead it goes, help! Your friend yells help, and it slows down and slows down. You see him first plunging towards the black hole, getting faster and faster, and he slows down, gets real red. I mean, from embarrassment. I mean, he's redshifted, gravitationally redshifted. The light leaving him has such a hard time struggling out of the intense gravity that it's weakened and reddened. In fact, time is slowed down. And what you see is your friend falls toward the black hole and slows down asymptotically to stop at a frightening place, the point of no return, called the event horizon. If you ever pass the event horizon, you will never return, because that's where escape speed reaches the speed of light. Now, you never see your friend reach the event horizon. You just see him slow down like crazy, turn super duper red. In fact, you can't really see him anymore. You got to use like radio waves, really long radio waves. But he freezes for eternity right outside the black hole. And you're thinking, like, that ain't so bad. I think I'll try that. And you turn off your jetpack and you start falling. You think it's going to be funny hearing your voice drop, kind of the opposite of a helium balloon. So you go, help, help, and your voice doesn't drop. But you heard theirs drop. And you think you're going to slow down. And you don't slow down. It just keeps coming. Oh, no. So you get real close to the black hole, and it's, oh, no, this is a trap. And when you're about 3 halves of, you're out about this far out, 1.5 times the radius, you fire the heck out of that jetpack. And for just a little bit, you manage to hover because you got some fuel left. And you're hovering right there. And you look around, and you're at a place called the photon sphere. The photon sphere is a place where photons, particles of light, can orbit. I'm falling and I can't get down. Photons orbit in the photon sphere. And that means if you're at the photon sphere and look this way, you might see a piece of light come into your eye that came from the back of your head. And you look over here, you see a piece of light came from the back of your head. You'll see your head out there in the distance, repeated like a hall of mirrors. And below you will be darkness. And above you will be the rest of the universe, kind of in a hurry, with the stars looking kind of blue and the planets going a little too fast and everything going a little crazy up there, because you're descending in a place where time goes slowly. And from where you are, it appears to go faster out there. It's getting weird. It's weirder because your jetpack sputters a little bit and you fall down some more. Now, the way I'm telling this story, it matters a whole lot whether or not your jetpack is on. I'm trying my best to tell it correctly for the case where you do still have a jetpack. As you continue to fall down towards the black hole, you fire the heck out of that jetpack. And you're descending slowly into the thing, fighting it every inch of the way. And you see the darkness, if I understand correctly, I think this is pretty sure this, folding up around you, leaving the outside world into an ever-shrinking tunnel of ever brighter, bluer, more intense light. And in that light, looking to the outer universe, you see the future of the universe flashing before your eyes. You're watching the future pass before your eyes in the outside world. If you suddenly discover you had an extra fuel tank and some incredible burners or something, you could blast back out of the thing, get safely away from the black hole because you didn't reach the point of no return yet, and you would find that you had traveled into the future. By how much? It depends. It depends on how much of your own subjective time you spent down there close to the black hole. It depends critically on just how close you got. I'll tell you that if you ever saw the movie Interstellar, I recommend it. It's weird. But there's a scene where some of the people go down to a planet. It's got big waves. It's just kind of all water. It's got big waves. And they're in a hurry trying to find if there's a place to live down there or something. And they leave one guy up on the spaceship up there. And when I go back up, they've only been gone an hour and a half, but he's been up there for 23 years. You know, he's old. And they were just down there for a little bit. And that's not just science fiction. That's what would happen. They were near a big old black hole called Gargantua, and a lot of technical details. And they had an expert, Kip Thorne's his name, expert in this stuff, helped him with the technical details, and it's actually plausible stuff. So I mean, it's hard. I mean, we don't have a place like that to go, but if it were there, this would happen. You know. Well, what if you don't get out? It depends on whether or not you turn your jetpack off or quit fighting. There's a lot of details that are extremely hard to imagine, hard to wrap your head around. There's videos on the internet where they try to explain it. I took a course called relativistic astrophysics. After I had my physics degrees from Tech, I went back and took a course at Georgia State, an 800 level course of relativistic astrophysics. They let me in the class. I wasn't even enrolled in the school. And I learned some of this stuff, and I kind of got it, but I mostly just got awed. In any case, one of the things I learned was what happens when you cross the event horizon. I don't know any better way to put this. Let me back up a second. There's a place you dare not go. It is the center of the black hole. It is called the singularity. It is a place, if it exists, and it's kind of like quantum mechanics gets involved, and can it really be a singularity or just almost a singularity, but in any case, close enough for our purposes. There's a place in the black hole where presumably the star or whatever matter was should have collapsed to. It'd be a mathematical point, or very close to it, with vast mass and near or infinite density. It is a place that would do just horrendous things to you if the black hole didn't rip you to shreds due to spaghettification. Tides. Talk about the ocean getting stretched. You get near a black hole that ain't kind of a small black hole, you're going to get spaghettified before you even get there. You'll be ripped into tubes of bloody pulp by the differences in the force on your feet and your head. Just shred you. Really big ones, though, you could safely approach. Really, really big ones like the size of our solar system. Billions of solar masses. But you don't want to go to the singularity. God, it's an awful place. You don't know what happens there. So you vow to yourself. You think, okay, I'm out of fuel. I'm going to fall in a black hole. But I'll tell you what, I may be trapped in this event horizon. I might be in here somewhere. But I ain't going to that singularity. I'll hang around the black hole forever if you want. But I ain't going to the singularity. So you think. Anyway, you're afraid of that place. Well, when you cross the event horizon, I can't say it any better than this. Space becomes time, and time becomes space. Space-time gets flipped inside out. And the point in the center of the black hole that you have feared spatially approaching is no longer a point in space. It is a point in time. It is the end of time. It is the apocalypse. The center of the black hole is your future. You cannot get out because you are drawn by gravity into the future. The force of gravity, once you're inside a black hole, becomes the river of time, flowing inexorably to the future, to the end. Now, there's one way out of a black hole if you get creative for a second. It probably doesn't exist. You probably don't have one of these. The only way out of a black hole is back in time. If you went into a black hole with a time machine that actually somehow worked, I don't even know what that would be, then presumably you could get out. It's one other idea. If the black hole's rotating, spinning, as they figured out as recently as as far back as 1962, that if a black hole's rotating, it takes on a different internal geometry, and the singularity can be kind of like a ring. And there's this, if I understand right, it's kind of like slipping through the ring. Conceivably, you could go through a wormhole. This is the stuff science fiction dreams are made of. You could go through a wormhole where instead of reaching the end of time, you'd pass through into another world. Maybe another time in our own universe, another place in our own universe, maybe another universe if such a thing exists. It would be a portal. God, that makes good science fiction, doesn't it? Yeah. Now, I tell you what, I've weirded you out really badly with the black holes. Let me tell you, they apparently exist. We think they do. Some of them are made of collapsed stars. We have evidence for them. We see things going around kind of like nothing, and what kind of energy coming up as these things gobble the heck out of stuff they eat. They're messy eaters as they eat stuff up. We also see in the center of galaxies colossal black holes. There's one about 2 to 3 million times the mass of the sun. in the center of the Milky Way. We kind of orbit it, but we orbit all that other stuff too, so it's not just it. We found them with masses up to maybe 16 like 16 billion times the mass of the sun in the centers of other galaxies, with stars and death spirals going around them. The orbits are a little different with Einstein and with Newton. You can actually spiral in if you get close with Einstein's gravity. And so that's weird. Let me go back to something, though. Remember, this is Einstein that came up with this stuff. And he looked at his math, and he saw the same problem Newton did in a little Einstein-y kind of way. Remember how Newton was afraid of the universe collapsing because of everything pulling on everything? Well, the same kind of thing happens in general relativity, the math of which I ain't getting to touch here. It's weird. But in any case, Einstein had the same problem. The universe appeared fated to collapse. And Einstein didn't like that. Now, Einstein's about as open-minded as anybody you're going to find. He really seriously thinks outside the box, but not on this. He wanted the universe to stay the same forever. So into his equations, he stuck a fudge factor, a constant, a thing that would take care of his problem. It was really a repulsive, cosmological repulsive force to prevent the collapse of the universe. He had no other reason to believe it except it looked like it could fit there, so he put it there. And about 3 years after he propped up the universe with this little constant called the cosmological constant, they found out the universe is expanding. Oh, Einstein didn't want to do neither one. The whole what goes up must come down thing? You see, with the universe, you can have the universe going up, meaning away from itself, after a Big Bang. Yep. You can have the universe flying apart. And either it could fly apart, the gravity from everything, and then you pull it back together again at the end of time. Or it could expand forever if it had its own escape speed. For over half my life, I remember trying to follow the details of whether or not the universe had its own escape speed. They found it was expanding. Einstein was wrong. The universe isn't just sitting there like that. It's flying apart. Edwin Hubble, who also was a boxer, he could knock you out. He knocked out the German heavyweight world champion boxer, because Edwin Hubble boxed. Space telescope's named after him. Anyway, Edwin Hubble found out the universe is expanding. And Einstein could have predicted the universe is expanding, and he undid his prediction with his cosmological constant, and then he felt stupid and called it the greatest blunder of his career. And in 1955, he died. In 1998, they were trying to figure out whether or not the universe had enough momentum, escape speed, to get away from itself and expand for eternity. And in trying to do that, they made some real careful measurements, and they found out, surprise, the universe is not slowing down like it should be. It's now accelerating. I say it's now accelerating because you can look out there into the past and see the past out in the sky. And they found out that the universe started to accelerate its expansion about 5 billion years ago, after apparently coming into existence 13.7 billion years ago. And there's some weird repulsive force driving it apart. Einstein's cosmological constant actually takes care of that. He may have been right after all. It's called dark energy now. It's a strange world out there. It's an incredible world. We live in it. It's ours, and yet it seems so alien to our thoughts sometimes. I've gone beyond what I really expect you to know. I just didn't want to leave it out. Please go read about it more if you're interested in these things. Or Zoom with me and I'll talk about it. I like talking about it. Anyway, my bottom line, I'm going to finish up with gravity right here. Newton came up with great stuff I'll test you on. Einstein came up with stuff beyond that I'm not going to really test you on, except maybe barely or something. It turns out Einstein's probably wrong. Does it ever end? Oh, no. The reason we think Einstein might be wrong is because there's this other thing called quantum mechanics that doesn't seem to mesh very well with general relativity. And there's this idea that somewhere out there, there's a theory to be found that will unify the big and the small, that will unify the cosmic in the submicroscopic world in a theory of quantum gravity. Maybe we'll live to see it. Anyway, we live in a phenomenal universe, and the universe is a concept that we can largely thank Newton for. Enough said about that. The next topic is another cosmic force that we're going to see.